You are being hit right now. Not metaphorically, not in some poetic sense. Physically hit. At this exact moment, invisible pressure waves are passing through your body, through your skin, through your organs, through your bones, through the fluid in your cells. Everything you are made of is vibrating in response to sound. Right now, as you sit there. And most of it you cannot hear. Most of it you do not feel. But it is happening regardless of whether you perceive it. Sound does not stop at your ears. It never did. I have spent my career thinking about the structure of matter, about what things are made of at the deepest level and how energy moves through them. And sound kept presenting itself to me as one of the most misunderstood phenomena in everyday life. Not because people are ignorant of it, because they are too familiar with it. Familiarity is the enemy of understanding. When something is present every moment of your life, you stop asking what it actually is. You stop asking what it is actually doing. I'm going to tell you what sound actually is, what it does to matter at the atomic level, what it does to your body specifically, why certain frequencies are capable of things that will disturb you, and what all of this reveals about the nature of waves, of matter, of energy, and of the physical world you are embedded in every moment of your life. Let us start at the beginning. Let us start with what sound actually is, because the answer is stranger than most people realize. Sound is not a thing. It is not a substance. It is not a fluid or a particle or a ray. Sound is a disturbance, a pattern of compression and rarefaction moving through a medium. When something vibrates, a speaker cone, a vocal cord, a struck bell, it pushes against the air molecules nearest to it. Those molecules get compressed together. They push against the next layer of molecules. That layer compresses and pushes the next. The compression propagates outward through the medium like a wave of crowding moving through a dense crowd when someone at one end pushes. Behind each compression comes a rarefaction, a region where the molecules have spread slightly apart, slightly below normal density. Compression followed by rarefaction. High pressure followed by low pressure. Oscillating outward from the source at the speed of sound, which in air at room temperature is about 340 meters per second. Notice what is not moving. The air molecules themselves are not traveling from the source to your ears. Each molecule just oscillates back and forth around its resting position, pushed one way by the compression and pulled back by the rarefaction. What travels is the pattern, the wave. The disturbance propagates through the medium while the medium itself stays roughly in place. Sound is not matter moving. Sound is a pattern moving through matter. This distinction matters enormously because it means that sound is not carrying pieces of the source to you. It is carrying information about the motion of the source. The pattern of compressions and rarefactions encodes the motion of whatever created them. Your ear decodes that pattern back into a representation of the original motion. The sound of a violin string is not pieces of the violin traveling to your ear. It is a pattern of pressure variation that your auditory system interprets as a violin. Now, what does this pattern do when it encounters your body? Your body is not a wall. It is not a hard boundary that reflects sound. Your body is a complex medium, a collection of tissues with different densities, different elasticities, different acoustic properties, and sound waves travel through it, around it, and into it depending on the frequency, the intensity, and the geometry. At the frequencies of normal speech and music, the sound waves that reach you from outside pass partly into your body and partly reflect off it. The reflected fraction is what gives you your acoustic presence in a room. The fact that you absorb some sound and reflect some is what acoustical engineers call your absorption coefficient. But the transmitted fraction enters you. It propagates through your skin, through the subcutaneous fat and muscle, into your organs and bones. At the frequencies of ordinary sound, the absorption is high enough that the waves lose energy quickly and do not penetrate deeply. But they penetrate. Every sound you have ever heard has entered your body, not just your ears, your whole body. This is not a dangerous thing at ordinary sound levels. The energy carried by ordinary sound is small. Conversation level sound carries roughly 1/1,000,000th of a watt per square meter of intensity. That is an almost unimaginably small amount of energy. Your body absorbs some of it, converts it to a tiny amount of heat, and the effect is negligible. But the principle is real. The energy is real. The interaction is real. Now let me tell you what happens as the intensity increases, because this is where the physics becomes genuinely disturbing. Sound intensity is measured in decibels, which is a logarithmic scale. Every increase of 10 decibels represents a tenfold increase in intensity. Normal conversation is about 60 decibels. A rock concert is about 110 decibels. That is not 50 decibels more intense than conversation. It is 100,000 times more intense. The logarithmic scale compresses an enormous range of physical intensities into a small range of numbers, and this compression hides how extreme the differences actually are. At high intensities, sound waves carry enough energy to do real physical work on the matter they pass through. The compressions and rarefactions are no longer gentle oscillations of pressure. They are significant mechanical forces applied to every surface and every volume the wave passes through. At 150 decibels, the level near a jet engine at close range, the pressure variations in the wave are large enough to cause pain, disorientation, and physical damage to tissue. At 190 decibels, the rarefaction phase of the wave drops the local pressure below zero in absolute terms, which in a liquid causes cavitation, the formation of vacuum bubbles that collapse violently. In tissue, cavitation causes direct physical destruction at the microscopic level. Sound, at sufficient intensity, tears matter apart. Cavitation is one of the most violent phenomena in ordinary physics. When a sound wave passes through a liquid and the rarefaction phase drops the pressure low enough, the liquid literally tears itself apart. A tiny bubble of vacuum forms. Then the compression phase arrives, and the surrounding liquid rushes in to fill the vacuum. The collapse is extraordinarily rapid and violent. The liquid converging from all sides reaches the center at high velocity and stops suddenly. The kinetic energy concentrates into a microscopic point. The local temperature at the collapse point can reach thousands of degrees. A tiny shock wave radiates outward. The bubble has become, for a fraction of a microsecond, something almost like a miniature explosion. This is not theoretical. It is well documented and extensively studied. Cavitation caused by sound, acoustic cavitation, is used deliberately in medical ultrasound procedures to break up kidney stones without surgery. Focused ultrasound at high intensity creates cavitation bubbles precisely at the location of the stone. The collapse of those bubbles fragments the stone mechanically. The same phenomenon that causes propeller blades on ships to erode over time, cavitation damage, is being harnessed as a surgical tool. Sound tearing matter apart, used to remove matter that should not be there. But I want to go deeper than the macroscopic effects, because what sound does at the macroscopic level, moving air, vibrating eardrums, even causing cavitation, is interesting but not the deepest part of the story. The deepest part requires going down to the atomic level, requires asking what a sound wave actually is when you look at it from the perspective of quantum mechanics. What is a sound wave, really, at the level of atoms? At the atomic level, a solid is not a collection of spheres sitting still. It is a collection of atoms connected by chemical bonds that act like springs. Each atom is constantly vibrating, oscillating around its equilibrium position, driven by thermal energy. At room temperature, atoms in a solid are vibrating billions of times per second with amplitudes of a small fraction of the intraatomic spacing. The solid is not still. It is a seething, vibrating lattice of atoms, all in constant motion, all connected to their neighbors by elastic bonds. A sound wave in a solid is a coordinated disturbance of this lattice. Instead of each atom vibrating randomly and independently, a sound wave imposes a pattern. Atoms in one region all move in the same direction at the same time, compressing the lattice. Then the region of coordinated compression propagates through the material. The atoms are still vibrating, but their vibrations are now partially synchronized, correlated across many unit cells, forming a wave. In quantum mechanics, this coordinated lattice vibration is quantized. Just as light is quantized into photons, discrete packets of electromagnetic energy, sound in a solid is quantized into phonons. A phonon is a quantum of lattice vibration, a discrete packet of sound energy propagating through a solid as a quantum mechanical excitation of the lattice. Phonons are not particles in the way electrons or protons are particles. They are quasiparticles, emergent quantum mechanical objects that arise from the collective behavior of many atoms. A single phonon is not localized at one atom. It is spread across the entire lattice, a wave of coordinated vibration that has a definite energy and a definite momentum, but no definite position. It is, in the most precise sense, a quantum of sound. The sound passing through your bones right now is, at the quantum mechanical level, a flow of phonons. Discrete quanta of vibrational energy propagating through the crystal lattice of your bone mineral. Each phonon carrying a specific amount of energy. Each one a quantum mechanical excitation spread across millions of atoms. The ordinary, everyday sound of the room you are sitting in, translated into the language of quantum mechanics, is a rain of phonons moving through the crystalline structure of your skeleton. Your bones are a quantum mechanical sound conductor. Right now, phonons do more than just propagate sound. They are responsible for heat conduction in nonmetallic solids. When one end of a piece of glass is heated, the thermal energy propagates to the cold end as a flow of phonons, high-energy lattice vibrations moving through the material. The thermal conductivity of a material is, at the microscopic level, the rate at which phonons can travel through it. Materials that conduct heat well are materials through which phonons travel easily. Materials that insulate are materials where phonons are scattered frequently and travel slowly. Phonons also interact with electrons. In a metal, electrons moving through the lattice can absorb and emit phonons, exchanging energy with the lattice vibrations. This interaction is responsible for electrical resistance. When an electron moving through a metal collides with a phonon, it is scattered, its direction of motion is changed, and this scattering is what we experience as resistance to the flow of current. The reason metals have higher electrical resistance at higher temperatures is that higher temperatures mean more phonons, which means more electron-phonon scattering, which means more resistance. And here is something that took physicists decades to understand. In certain materials at low temperatures, electrons do not just scatter off phonons. They attract each other through the exchange of phonons. Two electrons, which normally repel each other because they both carry negative charge, can be drawn together by a phonon-mediated interaction. One electron distorts the lattice as it passes through, creating a region of slight positive charge. A second electron, arriving slightly later, is attracted to that positive charge. The two electrons become correlated through the phonon field. They form what is called a Cooper pair. Cooper pairs are the basis of superconductivity. The quantum mechanical pairing of electrons mediated by phonons, by sound quanta, is what allows certain materials to conduct electricity with absolutely zero resistance at low temperatures. Sound, at the quantum level, is the mechanism that makes superconductivity possible. The most exotic electrical phenomenon we know of, the one that physicists have spent decades trying to achieve at room temperature because it would revolutionize energy transmission, is caused by the quantum mechanical interaction of electrons with phonons. With sound, I find this connection extraordinary. The everyday phenomenon of sound, the thing you hear when someone speaks, the thing that enters your body as you sit reading this, the thing you have known since the moment you were born, is, at the quantum level, the mechanism responsible for one of the most remarkable phenomena in condensed matter physics. The mundane and the exotic connected by the same underlying quantum mechanics. Let me come back to your body, because I want to tell you about something that sound does to biological tissue that most people have never considered. Your body is not made of one material. It is made of many materials with different acoustic properties. Skin, fat, muscle, bone, blood. Each one has a different density and a different elastic modulus, a different resistance to compression. And when a sound wave travels from one material to another with different acoustic properties, something happens at the boundary. Part of the wave is transmitted into the new material. Part of it is reflected back. The fraction transmitted and the fraction reflected depends on what physicists call the acoustic impedance mismatch between the two materials. The acoustic impedance of a material is the product of its density and the speed of sound in it. Air has very low acoustic impedance. Bone has very high acoustic impedance. The mismatch between air and bone is enormous. This is why sound from outside your body does not efficiently enter your bones directly. The impedance mismatch at the air-skin boundary reflects most of the energy. But sound traveling through your soft tissues, which have acoustic impedances much closer to each other, propagates much more efficiently from tissue to tissue. This is the physical principle behind diagnostic ultrasound. Medical ultrasound uses sound waves at frequencies of 1 to 20 megahertz, millions of cycles per second, far above the range of human hearing, to image the inside of the body. The ultrasound transducer sends a pulse of high-frequency sound into the body. At every boundary between tissues with different acoustic impedances, some of the sound is reflected back. The transducer detects the reflected pulses and measures how long each one took to return. From the travel times and the known speed of sound in tissue, a computer reconstructs an image of the internal boundaries. The image you see on an ultrasound screen is a map of acoustic impedance boundaries inside the body. Every interface between tissues with different densities and elasticities shows up as a reflective surface. The image is built entirely from the pattern of sound reflections. You are seen inside a body using the same physics that governs the echo of a shout in a canyon. Sound bouncing off boundaries. Travel time measuring distance. The image assembled from echoes. And here is something I want you to think about carefully. The ultrasound frequencies used in medical imaging, 1 to 20 megahertz, are sound. They are pressure waves in matter, the same phenomenon as the sound of a voice or a musical instrument, just at much higher frequency. The difference between audible sound and diagnostic ultrasound is not a difference in kind. It is a difference in frequency. The physics is identical. The wavelength is shorter at higher frequency, which means the waves can resolve finer details, smaller structures, which is why ultrasound can image internal organs. But it is the same phenomenon, the same pressure wave, the same phonons at higher energy. Now let me tell you about something that disturbs me more than the rest. Something that sits at the boundary between the well-understood and the not yet fully understood. Something that reveals how much energy sound can concentrate and what that concentration can do. In 1934, a physicist named H. Frenzel and his colleague H. Schultz were doing an experiment with ultrasound and a tank of water. They noticed something unexpected. Tiny flashes of light were being emitted from the water in the ultrasonic field, not from the transducer, from the water itself. Light was coming out of sound. Sound was producing light. In water. In a laboratory tank. The phenomenon is called sonoluminescence. Sound-induced light emission. It was documented, studied, occasionally reproduced, and then largely ignored for decades because nobody could adequately explain it. Then in the 1980s and 1990s, experimenters learned to trap a single cavitation bubble in a standing acoustic wave and keep it oscillating stably. The single trapped bubble would flash with extraordinary regularity, once per cycle of the sound wave, millions of times per second, emitting a brief pulse of light so consistent that it could be used as a clock. The light comes from the collapse. When the compression phase of the sound wave collapses the bubble, the violence of the collapse concentrates energy so intensely that the gas inside the bubble is heated to temperatures estimated at tens of thousands of degrees, comparable to the surface of the sun. At those temperatures, the gas partially ionizes into plasma. The plasma emits light, and then the bubble re-expands in the rarefaction phase, cools, and the cycle begins again. Sound, ordinary acoustic pressure waves, concentrating energy so intensely that they create a plasma at the temperature of a stellar surface. Inside a bubble smaller than a grain of sand, millions of times per second, in a glass of water, on a laboratory bench. The universe has a habit, which I have noticed throughout my career, of hiding extraordinary things inside ordinary phenomena. The deeper you look at anything, a proton, a glass of water, a mirror, a sound wave, the stranger it gets. The ordinary is always a surface, always a simplified approximation of something richer and more complex underneath. Sound is not just vibrating air. Sound is phonons and quantum mechanics and superconductivity and cavitation and sonoluminescence and plasma and the collapse of bubbles at stellar temperatures. And it is passing through your body right now. Every time you are in a room with sound, which is every moment of your waking life and most of your sleeping life, pressure waves are moving through your tissues. At ordinary levels, the effects are negligible, but they are not zero. The energy is absorbed. The tissues vibrate. The phonons propagate through your bones. The pattern of pressure variations is decoded by your auditory system into the experience of hearing, but the physical interaction is not limited to your ears. It happens everywhere the wave reaches. And there are frequencies that interact with the body in ways that go beyond what most people know. Infrasound, sound below the range of human hearing, below 20 hertz, can travel enormous distances because it is absorbed very weakly by air. Frequencies around 18 to 19 hertz have wavelengths comparable to the dimensions of the human thoracic cavity. There is evidence that these frequencies can induce resonance effects in the chest and abdomen. Feelings of unease, disorientation, a sense of presence, effects that have been reported in certain buildings, near certain industrial equipment, near certain natural sources. The mechanism is mechanical resonance. The pressure wave at the right frequency, matching the natural vibration frequency of a body cavity, driving it into larger amplitude oscillation. Some of what you have felt as unease in certain places may have been infrasound. Pressure waves below your hearing threshold, vibrating your body at its own resonant frequencies. I want to close with the thought that has always struck me most forcefully about sound. Not the physics of cavitation or phonons or sonoluminescence, as extraordinary as those are, but the simple fact that sound is a physical interaction between you and everything that makes sound around you. When someone speaks to you, the air pressure variations produced by their vocal cords travel to your body and physically move your tissues. Your eardrum moves in response to the motion of their vocal cords. The pattern of their vocal cord motion is encoded in the pressure wave, transmitted through the air, decoded by your auditory system, and reconstructed as meaning in your mind. That chain of physical events, from vocal cord to pressure wave to eardrum to nerve signal to conscious experience, is one of the most extraordinary things that happens in ordinary life. A mechanical disturbance propagating through air, carrying enough information to transmit thought from one mind to another. Sound is the physical medium of language, of music, of warning, of comfort, of everything that passes between people through the air. And underneath all of that, underneath the meaning, the music, the communication, is a pressure wave, compressions and rarefactions, phonons, quantum mechanical lattice vibrations, energy concentrating in collapsing bubbles until it reaches stellar temperatures. The same phenomenon from the conversation in a quiet room all the way down to plasma and light in a laboratory tank. The sound in the room around you right now is doing something to your body. It is moving your tissues, propagating through your bones as phonons, being absorbed and converted to heat at a rate too small to feel, but real nonetheless. The ordinary air around you is in constant mechanical contact with every surface of your body, transmitting to you the vibrations of everything that moves nearby. You are never isolated from sound. You are never isolated from the physical world. The pressure waves find you wherever you are. They pass through you. They leave you slightly different than they found you, by an amount too small to measure, but too real to deny. That is what sound is, not what you hear, what you are immersed in, what moves through you, what connects you, physically and mechanically, to everything around you that vibrates, which is everything, always.